Hello everyone and welcome back. So in the last class we had talked about your simple regression model. Okay, regression model. So I tried to explain what this model is about, how we had formed the model. So the model looked like this: y is equal to beta naught plus beta 1x plus your error term. So your y is the dependent variable, your x is the independent variable, and we try to find the relationship between y and x, how y changes as we change x. Okay, so your error term is basically all other factors that might affect y that we don't want to uh, allow to affect this relationship that we are trying to calculate. Okay, so we put or we bundle that in a separate term, that is your error term. So this was the model. Okay, so we had also talked about how this model answers three specific questions or three issues that we might face while trying to estimate this relationship between y and x. Okay, so the three issues were: how do we allow other factors to affect y? So basically, what we are trying to track here is a relationship between, or how y is affected by x, but there might be other factors that will be affecting your y. So how do we track those? So that is basically through your error term. Okay, just mind the circle. Okay, it's like a little bit bigger. So the second thing that the second issue that the model tries to solve is the functional relationship between x and y. So the model is a linear model, so the relationship between x and y is a linear relationship. So we are basically uh, dealing with a linear model here. Okay, so the third question was, how can we capture a ceteris paribus relationship between y and x? So we had proved this thing also in the previous video, how we so ceteris paribus is basically this condition where other factors remain unchanged. Okay, so if I have to change, or if I have to capture a change in the model, so I will do this to measure, sorry, this is your plus sign and delta u. So I know this will be 0, this will be beta 1 delta x or x, and this will also be 0. So delta y is equal to, or delta y is equal to beta 1 delta x. So this is how the ceteris paribus condition is also being fulfilled by the model. So in the case of ceteris paribus, your all other factors are fixed. So anything that is fixed, it will not change, and that is why we get this 0 over here. So your model, or the change in y, or the change in your dependent variable, is only coming through the changes in your independent variable. So that is also being captured by the model. So these were a few things that we had discussed about the model. So let's uh, talk about certain issues that we might face while dealing with a simple regression model. So y is equal to beta naught plus beta 1x plus u. Okay, so this is your model. So if I have to show you the model graphically, what is happening is, so this is your y, this is your x. So I have different values of x. Okay, x2, x3. So and this is your, suppose this is the relationship, and this is the model for your populations. So we'll talk about the sample separately. So this is the model that is representing your entire population. Okay, so we are not talking about the sample here. So we take different values of x, and for every x value, we get a value of y or an average value of y that is representing the entire population for that particular value of x. So for x1, I can have different values of y1, but my average value will lie on this line, that is your function, your regression function. So this is true for every x1. So whatever other values that I get, so for supposingly, if I have to let me give a practical example. If I have to mm, calculate the relationship between your salary is equal to beta naught plus beta 1 years of schooling, okay, and your u, let's take this as intelligence. So if I take x1 equal to 5 years of schooling, so I will get a certain value of y, say suppose here. And if I take x1 is equal to, so this is this x1 equal to, when x1 is equal to 5, the value of y that I get is for one individual. So as I take different individuals with the same x1, I will get different values of y. For every individual, given x1 equal to 5, the value of y will vary because I have an error term. So depending on the level of intelligence. Okay. So if supposing, and so this is the case for x1, and if I have to do this for the entire population, I will get different values of y, okay, for the same value of x1. But there will be an average value of y that will represent the entire population average for a given x1, okay, and that will pass through your simple regression function, that is the model that you have created, okay. So this gap between uh, the value of y for a given x1 and the average value of y that is representing the entire population, that is your error term or u, okay. So this is the sorry, let me rub this. This is the graphical or practical way of looking at u, okay. Just so I think there's some issue. I hope you understood what I was trying to tell you here. So I was just trying to give you a graphical view of how, or more practical understanding of how you would look like. So this is, just give me a moment. So this is how your u will look like, okay. So the problem that we'll face is, so we say that u is everything else that might affect y other than x, okay. So we, if u is everything else that might affect y, yet we don't know what you can be or what exactly can uh, belong to you. So this is a situation that we come across while dealing with the model, okay. So how do we deal with this situation? So one of the assumption that we make, since we have no idea what all things can come in u, so we assume that the average or expected value of u is equal to 0. So this is an assumption that we deal with in the model, as in, like, uh, since we are student of economics, so every model that we have ever studied has always been based on certain assumptions, right? So assumptions are a part and parcel when it comes to studying economics. So in this model, we assume that the expected value or the average value of u is equal to 0. What it means is that if this is x1, this is the population function, and I have different values of u for the same value of x. So the average, if I add all these terms, so sum, this is my expected value of y, average value of y. So if I add these terms, so some value, the some values of y would be less than the average, and some would be more than the average. So the average effect of all these uh, y values, okay, will be 0, or the expected value of error term will be 0. Like, s- if this is u here and this is u here, so suppose this is plus u, this is minus u, plus from the reference point is this point, okay? So this is plus u, this is minus u. If I add these values, the expected average value will come to be 0. So the model is created in such a way that this assumption holds, okay? Your expected value of the error term is equal to 0. So this assumption is, so you might be wondering, like, why are we taking this assumption and what would happen if we didn't assume this thing? So this is a very harmless assumption. Like, even if you try to break the assumption, you still will not face any issues. So the entire purpose of our conversation is, sorry, so the entire purpose of y is equal to of our conversation here is plus u. So this is the model. The model is created to mm, look into the dependence of dependence of y on x. So we have to check how y is dependent on x given other things constant. Okay. So what we are interested in is in estimating the value of beta 1. Beta 1. Okay. So we have to find this value. So if we assume the expected value of u equal to 0, or if suppose this value is not equal to 0, uh, will this affect my finding of beta 1? So let us check this thing. So if we assume that expected value of u is 0, okay, and if I do this, if I take the expected value of given x, beta naught plus beta 1 plus expected value of u. So okay, let me just, hold on to this. We'll get back to this equation. Okay, so let me just prove you here that this assumption of e expected value of u equal to 0 is totally harmless, because if suppose I take expected value of u not equal to 0, say it is equal to some value alpha naught, okay, just suppose. So let us work with this and try to do some mathematics and see what happens, okay? So y is equal to beta naught plus alpha naught plus beta 1 x plus nu minus alpha naught. So what I've done here in the model is I've added a alpha naught and I have subtracted an alpha naught. Okay, so the entire equation is unharmed. Okay, now, so y is equal to beta naught plus nu naught alpha naught plus beta 1 x plus nu minus alpha naught. So this is my new error term. Okay, and if I take the expected value of u minus alpha naught, it will come out to be e of u minus e of alpha naught. So I have taken expected value of alpha naught equal to 0, or sorry, of uh, expected value of u equal to alpha naught. This means that alpha naught minus alpha naught equal to 0. So the expected value is still equal to 0, even if I change the model and do this mathematical rearranging. My expected value of the error term will still be 0. So doesn't matter it doesn't matter uh, what is happening to the error term, if it's equal to 0 or not, the expected value is 0 or not 0. Okay, what is really important is that your beta 1, which is here. So if I take the expected, uh, go back. If I take the expected value of this beta naught plus alpha naught plus beta 1x plus expected value of u minus alpha naught. Okay, so e of expected value of y is equal to beta naught plus alpha naught plus beta 1 x plus 0. We know that this is equal to 0 from here. So your intercept, that is beta 1, the area of our interest, is unharmed, even if we don't assume that the expected value of your error term is equal to 0. So what has really changed here is that your intercept has changed. Okay, it has increased by alpha naught. So if graphically, if I draw this, so the slope of the line will not change, only it will shift a little upwards or downwards depending upon the value of alpha naught. Okay, that is what has happened here, right? So let's move ahead. So let me write the model again. Beta naught plus beta 1x plus nu. So for the population, we assume that expected value of u is equal to 0. Okay, so this assumption will be really helpful in the upcoming topics that we'll discuss. Okay, so now the problem is, and the problem that we have to face here, and we have to solve it also, is that x and u can be dependent or related. Okay, so I had taken the example where I had taken x as years of schooling, and your u as intelligence. Okay, so your years of schooling might depend on your level of intelligence. So if you're intelligent, you might not attend as much schooling as other people might do, or vice versa is also true. So this interdependence between x and u, this can affect our model, because we are assuming x to be the independent variable, or we are taking x as the independent variable, and we want y to depend upon x, and we don't want x to be dependent on any other variable. Okay, so we try to try to minimize this interrelatedness. So this is one of our main aim. So we want our model to be totally unbiased. So we just want to capture how y is depending upon x. We and our is the independent variable. We don't want x to be depending upon something else. Okay, as of now in this model, because we have to estimate the relation between y and x. So how do we deal with this situation? So one thing that we can do is we can assume that we can assume that u and x are uncorrelated. Okay, this is one thing that we can do. Just like we assume that the expected value of the error term is equal to 0. So this is something we can assume. So covariance of u comma x is equal to 0. But the problem here is that this shows that shows that there is there is no linear dependence between between x and u. But but the problem is that we can have any other sort of dependence that is not linear. So there can still exist a non-linear dependence. So dependence. So we don't want this, right? We don't want this. We want our estimate to be totally unbiased, and we don't want this to happen. So what is the solution that we have? So another thing that we can do is, so we, instead of assuming the covariance between u and x equal to 0, we can assume that the expected value of u given a value of x is equal to the expected value of u. So the expected value of u given a value of x from the population, okay, is equal to the average value of u for the entire population. I hope this makes sense. Just I'll repeat this thing. The expected value of u given x, okay, the expected value of u given x is equal to the expected value of u for the entire population. So I'll explain this. So what this mean is u is mean independent independent of x. So I take different values of x, okay, and I then I for every x I take the expected value of u given that x value. So the value that I get will be equal to the value of u for the entire population. Okay. So suppose from the example that we had taken, I take E given intelligence slash 5 years of schooling. Okay. So the expected value of intelligence given 5 years of schooling is equal to the expected value of intelligence given 7 years of schooling is equal to expected value of intelligence given 9 years of schooling, or whatever, dot dot dot, this can go on, and it is equal to the expected value of intelligence for the entire population. So whatever level of schooling I'm looking at, and whatever expected value of intelligence that I get for any level of schooling, that is equal to the expected or the average level of intelligence for the entire population. Okay, irrespective of the level of schooling. So this is the assumption that we are making here. Okay, and let's see how this helps us. Okay, and this is a very important assumption, and we'll try to see how this is going to help us sort the model in a better way. Another example, if you still seem lost here, let me bring another example. So if suppose u is land quality and your X is fertilizer amount. So expected value of U given x1 amount of fertilizer is equal to expected value of U given x2 amount of fertilizer, and dot dot dot, this can go on, is equal to expected value of U, that is the land quality. So land quality given x1 amount of fertilizer or any amount of fertilizer is equal to the expected value of the land quality in general for the entire population. So this is what this thing means here. Okay. Now I know that E of U via given x is equal to expected value of U. Okay. So this is, I have assumed, and I have already known this thing, that it is equal to 0 from the assumption I had made for the population. Assumption for the entire population. So this implies that expected value of U given x is equal to 0. So the thing that I was trying to prove here, so that is why I had to uh, cut that equation that I was writing in a previous slide, that x. So this is x, okay. So whatever values of U that I get given this value of x, the expected value of uh, the error terms will be 0. So whatever u values I'm getting here, okay, different u values for this same value of x for different people in the population, okay, so the expected value will be equal to 0. So I'll always be somewhere here. My value of y, or my regression function, or the linear regression function, will always pass through these points, these average points where the expected value of the error term is equal to 0. Okay, so this is what it is trying to explain. This is also called your zero conditional mean assumption of simple linear regression model. Regression model. Okay. So now if I take y is equal to beta naught plus beta 1x plus nu, okay, and I take expected value of y given x is equal to beta naught plus beta 1x plus expected value of u given x. Why? Because this is the model, this is your x, okay, and this is your y. So for every value of x there will be a corresponding value of y. That is why expected value of y given x. So expected value of beta naught is beta naught, and the same is the expected value of x is equal to expected value of x. So the model becomes that expected value of y given x is equal to beta naught plus beta 1x. Okay, so this assumption, just make uh, my working very simple with the model. And so this is the equation of a straight line, right? With each point on the line representing average value of y for that given x, okay, right? Different values of y for different x. So this is how the model gets simplified, and the result is uh, easy to analyze and easy to contemplate with the help of this equal to 0 assumption, right? So this was the issue with the model, that we have tried to sort with the help of an assumption, and the result that we get is in front of you. Like, we get a simple straight line output with the help of that assumption. So I hope this was something that got your attention, and you might have gained something out of this video. Um, so just think about it, think about everything that I've tried to mention here, and let's meet again. Till then, take care.